This talk is to be about vibrations and waves. And I'll start it by showing an experiment which shows the essential difference between vibrations and waves, and also the essential nature of the wave itself. I've got here a long, springy steel tape with a number of cross rods attached to it. Calling the rods numbers 1, 2, and 3, starting from the bottom, if we hold number 2 firm, we can make number 1 vibrate. That's a pure vibration because the steel spring tape between it and number 2 makes it vibrate backwards and forwards like a weight on a spring. But now, suppose number 2 were free and we displaced number 1 to one side. The twist of the spring between number 1 and number 2 would start number 2 moving and displace it. And at the very same time, the same twist would tend to stop number 1 and return it to where it was originally. In turn, the twist of number 2 would tend to twist number 3. It would start moving, and the back twist would tend to send number 2 back to where it was to begin with. So now, if we leave everything quite free and displace number 1, you will see the displacement running up the row of rods. There, that's a wave. I'm going to illustrate this wave traveling again by this apparatus I've got here. This very delightful model with which one can illustrate all sorts of wave properties is called the Vinome model. We've got a series of aluminium luffs. They're pivoted by a wire which runs along from one end to the other, and just on either side of the pivoting wire there's a spring, rather like the sort of spring one uses to net curtains. And that spring also runs along and connects each lath to the next, so that if one lath is displaced, it exerts a twisting force on the next one. Now again, if we hold one of these stationary, you see the connecting force because this just vibrates. But if now I let it free and move one in just the same way, that'll move the next, the next, the next, and you'll see the wave running along the model. There it goes, you see. Now, if we just damp that one and stop it, I'll do it again. I'll do a rather larger amplitude this time. There, you can see how clearly this is a better model for illustrating wave properties because the wave runs along quite slowly. And with this model, I now want to illustrate another phenomenon which shows the relationship between waves and vibrations. If I start a series of waves running along towards the end of this model, they will be reflected at the end and come back. What I want to show you is that if you have two sets of waves of the same amplitude and wavelength, but moving in opposite directions, they create standing vibrations which are like the nodes and loops, for instance, in that Kunst tube I showed you. You watch now. I'll set these waves going along, and this time I'll let them come back again from the end. There they go. You see I've created standing waves now in here. Right. Now, how does that happen? What's the explanation of that? It's interesting because it shows us the relationship between waves and vibrations. Suppose we have, in my drawing here, two sets of waves, but running the top one to the left and the bottom one to the right, of course with equal speeds. When momentarily they are in that position, they will add together their effects. Each wave will be making the upwards there and downwards there, so that whatever is displaced, like these laths, for instance, the displacement will be a large displacement down, up, I'll represent it like that, you see. And adding that to that one will produce that. Now, when each of the waves has gone a quarter of a wavelength, this one to the left, and that one to the right, can you see now they're just going to cut each other out, because where there's a crest there, there's a trough there. So the net result, when they've gone on a quarter of a wavelength, is nothing. There it is. Now, let's move them on another quarter of a wavelength, to there and to there. You see they'll now add together again, but this time they will add together in such a way that there's a both troughs add together to put a big trough there. Both crests together make a big crest there. So the result, the displacement of the rods will be first that, then that, then that. Let's put them all on top of each other, and you see that is just what we call a standing wave. There it is. Those are those vibrations backwards and forwards that you saw just now made by the rods. Let's do this just once again. Now you've seen that. I'll start a rather quicker one this time, and you see if we have shorter waves, we have, of course, shorter standing vibrations. There we've broken it up into shorter standing waves, you see. And the point is that always when you have nodes and loops, the wavelength, as you can see by looking at one of these, covers two of these loops. It goes from that point there to that point there. Two standing waves together make one wavelength. I now want to consider the relationship between wave velocity and wavelength and frequency. It's really a very simple one. Let's consider it, for instance, in the case of sound waves. Sound waves travel at about 1,100 feet a second. Now, suppose the sound waves which we are listening were 1 foot long. You can see that with this velocity, 1,100 1-foot waves will pass us in a second. In other words, the frequency will be 1,100. If the waves were 2 feet long, there'd be 550 of them in 1,100 feet. So the frequency now would be 550. Let's illustrate that by one or two experiments. The first experiment I got here is one called Milder's experiment. We have a string. It's attached on one side to a vibrator there, and on the other side it's hooked over a pulley, and we can put different weights on that little arrangement at the end of the string. Now, suppose that the string is very slack. Then waves only travel along it slowly. And therefore, if we set this vibrator going, and it's got a constant vibration rate, you'll see we'll get 2 complete waves, or 4 nodes and loops in the string. And then what I shall do is to put a heavier weight on, make the wave go rather faster, and you will see now we'll only get 3 nodes and loops, and finally by putting quite a heavy weight on, the wave will go past, we get only 2. There it is vibrating, you see, with 4 loops between one end and the other. Now, if a somewhat heavier weight is put on, waves are traveling faster, we've got 1.5 waves, if you remember the rule, 3 loops in between the points. And a still heavier weight, and we'll make the waves go faster still. I hope we're going to break down into 2. It's now vibrating, you see, in 2 nodes and loops. Now I can show it in another way by means of this tube, which I showed in a previous lecture, in which we have gas in this tube under pressure and a number of fine holes. Now that is just like the Milder string. If we set the oscillator going, it will break down into nodes and loops. But this time, we can't alter the rate at which the waves are traveling. That is the rate at which sound travels backwards and forwards in this tube. What we can alter now is the frequency. And I'm going to show you a simple experiment that's going to work this way. We'll first of all set this at a frequency so that there are 3 loops along the tube. Then we will run up the frequency so that there are 6 loops along the tube. Half the wavelength. Now, if you remember the rule, if we have half the wavelength, then twice as many waves will pass our ears in a second, therefore the note will go up in an octave. We'll illustrate that by 3 and 6, and then we'll try and do it with 4 and 8. And you'll see in each case we go up an octave. Right? We'll light the jets now. And Mr. Coates will set it vibrating so that we get these 3 notes. There they are. Now 6. Can you hear it go up the octave? Down to 3 again. That just goes up 1 octave, doesn't it? Now if we make it 4, there are 4. Now we'll ride up to 8, and there's our 8. 8 down to 4 again, and you hear it drop in its octave. So there you see those are illustrations. The shorter the waves, the higher the note. They're just in proportional to each other. Well, now I'm going to do another experiment to illustrate the relationship between vibrations and waves. It's a very important principle, this one. It's what's called resonance. If you have a vibrating body and give it a series of pushes at exactly the same frequency as the body itself wants to vibrate, then you can get it in a high state of vibration. If, however, the series of pushes that you give it are not in time with its own vibrations, they first of all will pull it one way, then another, and the result will be 0. Well, there's an extremely simple way of illustrating that. You've got a whole lot of rods here which are matched. Those 2 match each other in frequency, the yellows match each other in frequencies, and so do these orange ones. They're fixed to a baseboard here. Now, this baseboard is not quite rigid. A piece of rubber between the clamp and the table. So if one of these is vibrating, it can move the base a very little bit. And because the frequency of that matches that, it will start this one going when I vibrate this one. You'll see each will respond to its mate. I'll set the red one going first. You see the others stay quite still. It's only the other red one that moves. Here's the yellow one. And now the little orange one. There you see this one going when that one goes. That's, of course, what you're doing when you tune your radio set. You tune so the oscillation in the set corresponds to the frequency of the waves from the station you want to pick up. And therefore you build up the oscillation into a large effect. Well, here's another way of illustrating the same thing. This little model actually was made up to illustrate the way the ear works, but it's quite a good illustration of this principle of resonance. Mr. Coates has here a disc with a series of tremblers on it. Some of these tremblers are on short stalks and some on long stalks. The short one, of course, this is the one I'm pinging there, vibrates much more quickly than the long one at this end here. Behind this disc is a flywheel, and this flywheel has a slightly eccentric center of gravity, so that as it buzzes round, it shakes the plate a little bit from side to side. Well, we'll set this going, and then let the flywheel die down. And as it dies down, you will see these tremblers respond one after the other when the frequency corresponds. There you see the first one going there. Now there's the second one. 3, 4. We've not got them exactly spaced in timing. Yeah, this one's just coming on. Now that one, that one. Now this fellow here will come, and finally the very slowest. There. This then is another example of the way in which vibrations are picked up by resonance when the frequency is exactly right. Finally, here is an experiment, what we might call unlinked vibrations. I've got two weights hanging here. They're pendulums of the same length. So that if they were firmly fixed at the top, they would vibrate with exactly the same rate. They're not firmly fixed quite, because this little platform from which they're hung is slightly movable. So if this weight moves the platform, it moves the point of support of this weight here. Like my rods, if I set this going, this one will pick up the vibration by resonance. But now what I want you to watch is this. Battery set swinging. Energy must be supplied to set it swinging. It comes from this one. So the very effort of getting this one going will stop this one. Then this one will get, which is going quite hard, will begin to hand its energy back, and this one will start swinging. See, if I set them going like this, they hand the energy backwards and forwards. Now, do you see that one going there? And this one's slowing down. And presently, this one's going to stop altogether. And then the process will be reversed. Now, this has almost come to a stop. That one's doing it all now. Now watch the starting this one going again. In fact, these length vibrations are very interesting physically. They come in a number of physical problems. The point is that one of these alone, swinging, is not a fundamental vibration. A fundamental vibration is one that stays put, continues always. The two fundamental vibrations of this system are this one, when they swing in opposite directions, or this one when they swing in the same directions. And if you think that out, you can see that one alone is a combination of both, and that's why they're always handing over their energy from one to the other. And incidentally, this is the explanation of a very interesting conundrum. I don't know whether you've ever come across this. Why do grandfather clocks stop on Thursdays? This isn't a grandfather clock, but it's quite a good model of one. The point is this. First of all respectable grandfather clocks are 8-day clocks. Secondly, all respectable families wind up their grandfather clock on Sunday. The consequence is that by Thursday, the weights which come down so much every day to keep the clock going have just about got opposite to the pendulum. And like these two pendulums here, unless your grandfather clock is very firmly fixed to the wall, the weights will pick up the energy of the pendulum and so stop it. Here I've got this clock and can set the pendulum going, and this is about, say, Monday evening or Tuesday, where they've got to here, and there's very little effect on the weights, as you see. They're just coming down, and the weights are driving the clock. But now, luckily, I'll stop the pendulum. Luckily, if we don't have to wait 2 days over this, I'll make it Thursday by letting the weight come down. And now, because there's a little give in this clock, I think you'll see if I set the pendulum going, the weight is going to pick it up. You see it starting to swing, and a heavy weight on the end of the chain there would pick up so much energy, cause the pendulum to miss a tooth, and then, of course, it would stop. Therefore, you must fix grandfather clocks very firmly to the wall so that the pendulum cannot give its energy to the weight. Well, there are some illustrations of these relationships between vibrations and waves.